Good morning, everyone. I'm thrilled to welcome you all today. Today, I will be sharing my research work under the supervision of Professor Priyanka Verma. I'm excited to give you a brief overview of what we will explore together. We will look into the key aspects of my project, including the main objectives, methodology, and findings. I promise to keep it concise and engaging. So, without further ado, let's dive into the presentation. Let's take a closer look at the non-stoichiometric form of WO3. This variation is particularly interesting because it introduces oxygen vacancies, which significantly influence its properties. One key feature is its narrow band gap, meaning it can absorb a broader spectrum of visible light, making it highly effective for photocatalytic applications. Additionally, WO3X exhibits plasmonic properties, which enhance its ability to interact with light and improve charge separation, crucial for catalytic efficiency. The presence of active sites is another vital aspect, as these are the locations where reactions occur more readily, boosting overall activity. Compared to noble metals, WO3X is abundant and less expensive, making it a more sustainable and cost-effective choice for large-scale applications. These oxygen vacancies, often represented as WO3X, are fundamental because they modify the crystal structure and electronic properties, essentially creating more active sites and improving performance. Looking at the crystal structure of WO3X, we see how these vacancies are integrated into the lattice, which plays a crucial role in its photocatalytic behavior. Overall, WO3X stands out as an efficient photocatalyst because of these combined features: its unique electronic structure, plasmonic behavior, abundance, and cost-effectiveness, all contributing to its potential in sustainable energy and environmental solutions. Let's take a closer look at the characterization methods we've used for our PWO3X system. First, we have different forms of palladium and tungsten oxide. These variations help us understand how different modifications affect our catalyst's properties. Moving on to the techniques, SEM and TEM are essential for examining the surface morphology and particle size at the micro and nanoscale. Bed analysis provides insight into the surface area, which is crucial for catalytic activity. FTIR helps us identify functional groups and bonding environments, while XAS and XBS give us detailed information on the oxidation states and electronic structure of our elements. TGA allows us to assess thermal stability and composition changes. Motzkotky measurements help determine the semiconductor properties like flat band potential and carrier density. EPR reveals unpaired electrons, which can be linked to defect states or free radicals. UV-Vis spectroscopy provides information about optical properties and bandgap energies. PXRD confirms the crystalline phases present in our materials. Altogether, these characterization techniques give us a comprehensive understanding of our PWO3X catalysts, enabling us to correlate structure and properties with catalytic performance. This detailed analysis is fundamental to optimizing our systems for better efficiency and durability in applications. Now, let's take a closer look at the scavenger results, specifically focusing on catalysis. Here, we're examining the photocatalytic reduction of 4-nitrophenol to 4-aminophenol. As you can see, this process is significant because 4-nitrophenol is a common environmental pollutant, and converting it into 4-aminophenol, which has valuable applications, is a key step in pollution remediation. The results demonstrate how effectively our catalyst can facilitate this reduction under light irradiation. This ties into the overall theme of using advanced catalytic materials to address real-world environmental challenges. The efficiency observed here highlights the potential of our approach for practical applications in detoxification and sustainable chemical processes. For further details, please refer to the published article at the link provided. In conclusion, I want to emphasize the key points we've discussed today. We've explored how this research advances our understanding of the topic and the potential implications it has for the field. The most important concepts include the innovative approaches used and the significant findings that could shape future directions. Throughout this presentation, we've connected these ideas back to the overarching theme of advancing scientific knowledge and practical applications. Thank you for your attention, and I encourage you to review the article for a deeper dive into the specifics. Thank you for your attention. I'd like to take a moment to acknowledge everyone who contributed to this work. Their efforts have been invaluable in bringing this project to fruition.